Okay, a little bit late, but it's hard to do these videos. But I wanted to cover the material we would have covered yesterday in Monday's class. Please try to watch this before you come to class tomorrow. Just a reminder, on Friday we'll do in-class problems for Chapter 9. Remember that if you're not in class, that portion of that assignment, you can't get credit for that day, and your mastering homework will be due that Friday. Two things coming up, sponsored by the Physics Club. Thursday night, there's a movie night of Hidden Figures. Maybe you want to drop by McPhail's and watch that. And after break, to celebrate Pi Day a little bit later, since Pi's over break, you get a chance to try to Pi your professors on Thursday, March 19th in McPhail's. I know a couple of physics professors have volunteered, so you might want to check it out. All right, so let's get down to business. What we've been working on is finding the centroid of a body, which is the center of area. So if you have a volume or an area, which is basically we're going to do the area, the x-centroid will be found by taking a weighted average of a position times dA over dA. And the y value would be y tilde dA over dA. If we're talking about a line, this would change to dl. If you're talking about a volume, this would change to dV. So here are some pictures. We will be starting to use tables to give us values of centroids of common shapes so that we don't always have to do the math. And here are just a couple examples. I think I made copies of a table for you that I'll hand out to you that you can use. It's also in your book. So basically, there's steps that we do. Let's just look at this particular example. If we wanted to find the x-centroid of this blue area, it says we're taking x dA over dA. So that means that all the area, like if I take a strip like this, would have the same x value. And then we'd have to write this all in terms of the same variable and then integrate over the appropriate limits. If we wanted to do the y-centroid, the definition is similar, but because we want all the area to be at the same y value, we have to rewrite how we would write the area and, write everything in the right variables, which would, in this case, be in terms of y, and then integrate to find it. In class on last Friday, we did both of these examples, and we found that the x-centroid was 4/5 and the y-centroid was 2/7. Now I wanted to show you another way where we could find the y-centroid, which also could be another way to find the x-centroid, but we're going to do y as an example. This time, instead of requiring that the area dA all have the same y coordinate, which we're multiplying by in the numerator, we're saying that that y tilde is the centroid of the vertical strip, which in this case would be y top divided by 2, but sometimes the area might be bounded by a top and bottom curve. And so let's look at a good expression we can always use for the centroid of this vertical strip. The y centroid would be found by taking the value at the bottom of the strip of the area and adding 1/2 of the height of dA, which is y top minus y bottom. This would actually simplify to 1/2 y top plus y bottom. For this particular example, the y value at the bottom is 0, and that's why we can just write it like that. So we have y centroid can be written as the y top is x cubed and divided by 2 times dA over integral dA. Since it's been a day, I'll just remind you that we had written dA for the vertical strip as x cubed dx. It was this height, and this is the width. We also found that the integral of dA, which is the area, was 1/4. We don't have to redo all that calculation. So y, the centroid, is going to be the integral of x cubed over 2 times x cubed dx from 0 to 1 over the integral of dA, which we already just said is 1/4. So let's do the top integral. So when we worked it all through, it turns out that we got exactly the same value that we got before with a horizontal strip. And obviously we want to get the same value, otherwise something's wrong. Now let's see why we might want to do that. So here's a problem where we want to find the centroid, and but we're going to use it then to do a problem, because we're told that this steel plate, which has an irregular shape, is bounded by 2 different curves on the top and the bottom, has a uniform thickness though, and we're told its density. We need to find the center of mass, because this is where we would put the weight vector to do our calculations of our support reactions. First of all, I'm going to do the work of finding the total mass of this, because in order to find the weight vector, we also need to know its mass multiplied by g. That's going to be rho dv. I'm going to choose to use these vertical strips, which you're going to find out really quickly are the easy ones to do. The density is 7850. The volume is the thickness times dA. That's actually dV. and dA, which I just wrote. I'm going to put in a value for thickness. This is 0.3. And dA I would write as y top minus y bottom times dx. So the mass is going to be 0.3, 7850, and then the integral of square root of 2x minus a minus x, that's the height, times dx. So to simplify this, I'm going to just look at the integral. It's going to go from 0 to 2. Square root of 2 times x to the 1/2 plus x dx. So I've been able to find the total mass of this plate. Now I'm going to figure out the x-coordinate of its centroid. The denominator is the area which we just found. I'm only going to have to work on the top integral. And if we put in the values, we'll get the top. It's 5.888667. Centroid ends up to be 1.26 meters. Now we can also find the y centroid. And this is the one where we have to use the method that I just showed you with the different area. Normally we would do this for the y centroid, have all the area have the same y value. But the problem is I have different curves bounding it in the top and the bottom. So that's not going to work. We're going to need to use vertical strips. And this is where we're going to have the y centroid times dA over dA. with the y centroid is going to be 1/2 the y value at the top plus the y value at the bottom. This is still our dA. And our area is still 4.667. So the way this works out, this is just going to give us a difference of 2 squares. So if we just do the top integral, we're integrating 1/2 and then 2x minus x squared dx from 0 to 2. It's going to give us 4/6. So y centroid is 4/6 over the 4.667.143 meters. This is going to tell us exactly where to put the weight vector. This is the weight. And then we'll also have the reactions, AY and AX and B, which is in the normal direction. And then we would go through our normal equilibrium process to find those values. It turns out we didn't really need to use the y centroid. It doesn't ever enter into our calculations. But I wanted to see a problem where we had to do it. All right, so now we're going to extend this idea of finding a centroid to what we can call composite bodies, which are basically shapes that can be broken down into a combination of really simple shapes. And each of those individual pieces that make it up, it's pretty easy to find their centroids. And what we're going to do is divide up our object into those things, find individual centroids, and do a weighted average to find the overall centroid of the object. So here's just 2 examples of profiles we might be working with, like an I-beam, which is really just 3 rectangles. And we know exactly where their centroids are, but we would take each of those individual centroids. They would have to be located to an agreed upon reference point to give x and y values, and then we would weight each of those values by the area that they represent. Here's also some examples, and also brings up in this first example on the left, sometimes we have holes. So this pink area is really like a semicircle, a square, and a triangle, but then it has a circular hole. We can deal with holes by just assuming that their area is negative. And again, here is a centroid on the right-hand side. If something has a uniform thickness, in this case, in the z direction, we can just say that z coordinate is halfway along the total depth, so we don't need to do any calculations. But for the profile of the area shown in the xy plane, we need to find the overall centroid. And in this picture, they've separated this object into 3 rectangles, 1 tall and vertical in the middle, 2 off to the side, and 2 triangles that mirror each other. So just as we would find the center of gravity or center of mass of a composite body by, like, let's just say we have these discrete masses at certain locations, we would take their x, y, and z coordinates times their weight and then divide by the total weight. we would do something similar if we're finding centroids of areas. And if we find that it's a whole, if one of the pieces is a whole, again, that value, whether it be weight or mass or area, would be negative. So again, we have a series of steps. We want to divide the body into pieces that we know their shapes. Wholes will be negative weight or size. We make a table, and we want to put on that table for each object its weight, mass, or size, depending on what we're doing. And then the columns for their x values, their y values, and their z values. It makes it easier for us to keep track of the things that we're going to add up to find the overall centroid coordinates. Keep in mind that when you're finding the coordinates of x centroid, y centroid, etc. for each object, there is an origin on your object, and your piece might not be up against that origin, so you have to add the distance it is from the origin and then find the centroid from that. So finding these values for x, y, and z is a little bit more involved. So let's just look at an example. Oh, here's this table that I think I made copies for you. All right, so here's this shape. I'm gonna make it into, I'm actually gonna consider it the first, number one, is the entire rectangle. Well, it's a square. And then 2 is the whole. And then 3 is the triangle. I'm going to make my table for I, x sub I, y sub I, a sub I. So for number one, its centroid is, its x value is 1/2 of the base, which is 3 feet long, and it's in the negative direction. So it's minus 1.5. And in the y direction, it's positive 1.5. The area of this rectangle is 3 by 3. It's 9 meters squared. For number two, now, number 2 has a width in the x direction of just 1 foot, but I need to add this 2 feet to it to give the proper coordinate. So it's minus 2 minus 1, so it's minus 3. The y value, I have 1 plus 1 is 2 because I have to add this bit to it. And then it's in the middle here. I just found a mistake here. I should have added a half. So this is minus 2.5 for number 2. Because the width of it is 1. So it's only add a half of that to find the centroid. Its area is 2. But I should make it negative because it's a whole. 3 is just 1/3 of each side, measured from the thick end. So its x value is 1, its y value is 1, and its area is 1/2 3 times 3, which is 4.5. So now we can use all these values to find the x and y coordinates of the centroid. We're doing the sum of the x sub i's, area sub i's, over sum of area sub i's. So I get minus 1.5 times 9, minus 2.5 times minus 2, plus 1 times 4.5. On the bottom's all the areas. I have 9 minus 2 because it's a whole, and 4.5. I get an x value of minus 0.348 meters. No, feet. For the y value, you get 1.5 times 9 plus 2 times minus 2 plus 1 11.5. And the area is 11.5. The y coordinate is 1.2 feet. All right, that'll be it for today. We'll look at 2 more examples in class before we look at pressure.